Well, what fool in his right mind would use integration to do that then? Wouldn't you use geometry? Well, yeah. So if they really want me to prove that, I always believe in doing exactly what the instructions say. If I give you an instruction on a test that is not what I intended and really it lets you skate with only like writing, no solution or something like that, then you take advantage of that and saying, you know, Newberry was an idiot and I'm going to take advantage. Do that. And so I would do that here. The book was an idiot. They didn't say how to prove that formula. I wouldn't use integration to do that. Does anybody know how to get the formula for the sector of the circle? Maybe integration was the right way to go then. If you have a circle with a central angle, what's a central angle?
There is a formula for the sector. I remember always forgetting it.
I remember always forgetting it. I forget always remembering. So what was the central angle? Center or vertex at the center. So pretend that's what happened there. Poor misshapen creature. Just think what horrible things this circle must have gone through to look that bad. So there's theta. And say the radius is r. What do you do? Come up with that area formula? It's actually something we're going to need when we learn how to find areas in polar coordinates.
Oh, God.
So this is not just something I'm doing for fun here. We won't want to use calculus to come up with that formula. May remind me what we do. So let's let A be the area of this circular sector that we're trying to find. Well, I believe A, the ratio of A to the circle's area, should equal the ratio of theta to the entire circle angle. What is the circle's area? And so if I'm looking for a formula for A, I'm going to now multiply by pi r squared. So theta pi r squared over 2 pi. Is that right?
Mm-hmm.
Yeah. And so that's 1/2 r squared theta. No calculus necessary. Can somebody tell me how to get the formula for that arc length? Call it S. Same ratio, the ratio of theta, the angle of the sector, to the entire circle angle, right? It's 2 pi all the way around, is going to equal the ratio of that arc length in question to the entire circle circumference. So theta over 2 pi is equal to S over, and what is the circle's circumference? Yeah, well, usually they use radius. So we'll say 2 pi r. 2r is the diameter, but what you said is correct, of course. So S is r theta. All right, so don't do 35 the way that the book was trying to fool you into it. However, I believe, 41 is the one that I signed, isn't it? Did I sign 37? Did I sign 37? Yeah. Oh, I'm a jerk. Find the volume of the solid obtained by rotating about the x-axis, the region enclosed by the curves y equal 9 over x squared plus 9, y equals 0, x equals 0, and I think it was x equal 3, right? That's the region. The axis of rotation, I believe, was the x-axis? Yeah. So, I mean, I'm supposed to hold you responsible for graphing stuff like that, supposedly. I kind of hate to do that, but can someone give me any idea what that thing looks like?
Probability method.
What's that?
Probability method.
Well, if that x squared plus 9 was in the numerator, I'd agree to you. I agree with you. No, see, we have to think about that in the way that we learned to graph in Calc 1, or maybe even pre-Calc. What are the vertical asymptotes?
Positive.
Very good. Denominator's never 0.
Yeah.
Horizontal asymptotes. You don't need a limit. The degree of the bottom is bigger than the degree of the top. Yes, say it louder.
Yes, 0.
The x-axis, y equals 0. This function is always positive, isn't it? But I know that it gets infinitely close to the x-axis on the ends. So on the ends, it looks like this. In the middle, we may not be sure what it does, but we know that it doesn't double back on itself. It's a function, right? No loop-de-loops or anything like this. It can't write my name. It could have several maxes and mins, anything like that, but it's always up here. We don't know for sure. Actually, maybe from your prior experience, you do remember that it looks like this, sort of like a normal distribution in a statistics class.
Oh.
Y equals 0, x equals 0, x equals 3. So there's the region. We're going to rotate it around the x-axis. So it's going to generate something, oh geez, I got to try to draw that. We can't draw that. Oh well. Anyway, something sort of like that. It's circular in that fashion. So what do you want to use? Washer method, shell method? Well, I think I'd rather integrate dx. I don't want to solve that for x. It would generate radicals, wouldn't it? So that means I'd rather keep x's in there. So I want to integrate along the x-axis. That's parallel to the axis of rotation. So that's the disk in the washer method. So what I'm going to do is cut this thing and look at the disk that's generated. Notice that the radius is the y value of that point. So I'm going to do the integral from 0 to 3 pi r squared dx. And r is the y value. It's this junk, isn't it? So this is going to be pi integrals 0 to 3. When I square that, right, this is r. 81 over x squared plus 9 quantity squared. Well, I'm not going to square that thing out. That's square completed already. Rather than squaring it out, how would I resolve this integral? I'm going to factor out that 9. I'm going to make that into a 1 so that I can do a trig substitution. So I'm going to factor out that 9. Once I factor it out within this square, that's an x squared over 9 plus 1. Did I do that correctly? If I did, then that 9 once squared is going to cancel the 81, isn't it? So pi integrals 0 to 3. The 81 is now canceled. dx over x over 3 squared plus 1 quantity squared. And now we're going to make the substitution that x over 3 equals tan theta. So x is 3 tan theta. dx is 3 secant squared theta d theta. This better come out nice. I'm tired of doing ugly integrals. New limits of integration. When x is 0, theta is 0. When x is 3, the tan theta is 1, so that's pi over 4. Tangent of pi over 4 is 1. dx is all this crap. 3 secant squared theta d theta. Square, this is tan squared plus 1, so secant squared squared, secant to the 4th. So that's a cosine squared in the numerator. Right, because it leaves a secant squared in the denominator. So that we're going to generate a 1/2 when we use the power reducing formula. So I'm going to write 3 pi over 2. Integrals 0 to pi over 4, and that will be 1 plus, I got it right this time, cosine 2 theta d theta. And I'm going to assume you can finish because this problem sucked. So I certainly would be willing to give you a volume of revolution, but even though you're really supposed to be able to graph that, that would be kind of mean. I want to give you something a little easier to graph.
You always plug in 20 things.
Yeah, I know, but it's still kind of mean. I don't want to be mean to you guys. I don't mind being a little ugly. I have no choice. But mean, I don't have to be mean. I'll save that for, you know, the dog and the cats,
Wow.
you know, the kids and the wife, neighbors, people I work with, cops. Oh, wait a minute, you gotta be nice to cops. They carry guns. I keep forgetting that.
And they use them.
Yeah, they do, don't they?
You know in England cops don't carry guns?
I know that.
Go rob a bank.
Oh, good
That-
idea. You head over there and go for that. Make sure to send me $1 or $2, or £1 or so. So, they just don't carry guns on the beat. Don't worry, they have cops with guns, and they are trained to use them. 41. Frankly, I think they should all carry bazookas. A torus is a circle that is rotated around an axis, right? Better known as a donut, right?
Why is it called a torus?
I did not name it. It's not the same as a bull. That's Toro or Taurus. Right? This is T-A-U,
Yeah.
something like that. T-O-R. T-O-R-U-S. Torus is generated by rotating a circle about the x-axis. Find a volume enclosed by the torus. Screw that. I'm going to always center, if I'm going to rotate a circle, I'm going to center that circle at the origin. Heck with those guys. Much easier to do it this way. So here's a circle of radius r. Or actually, let's use little r. I think that's what they always do in the formula. And we're going to rotate that around a vertical line, capital R. Right? X equal capital R. This, once again, is a problem that supposedly you've done twice. You've done this problem with the disk washer method, and you've done it with shell. You were supposed to do them both in Calc 1. If your Calc 1 teacher didn't make you do that, then they fell down on the job. So I'm going to rotate that. And there's the circle generated, or the donut. Right? And I want to figure out the volume. So, what do you want to use? Disk washer, or do you want to use shell? How many want disk washer? How many want shell? Shell it is. I would have chosen shell anyway. It's an easier integral. So, and plus, notice it's a vertical axis of rotation, so shell will be right angles to that. It's an x integral, which is always a little more comforting, right? So if I'm going to integrate x and use the shell method, then that formula is 2 pi integrals radius times height dx. What will be the limits of integration? Look at the region being rotated, the original circle. And I want to know what's the smallest x, what's the largest x? Negative little r to positive little r. And radius and height of what?
The shell.
A typical shell. So somewhere from minus r to r, I need to pick an x and draw a line segment there. So I ought to pick an x that's easy. I think I'd prefer to pick an x that's in the positive region. So I think I'll pick this x. And I will rotate that infinitely thin line segment. Notice how it's infinitely thin? So I want to know what's the radius and height of that. All right, 2 pi integrals minus little r to plus little r. And let's see, the radius, well, this point has coordinates x comma y, doesn't it? That means that this distance is y, and this distance is x. So I can now see that the radius is capital R minus, what did I draw? God bless America, dyslexia rears its ugly head. Jeez. How did somebody dyslexic ever get a master's degree in mathematics? I probably cheated. Cheated my way through. So the radius is capital R minus x. Because this distance is capital R. I want this distance, so I got to take x away. The height is 2 times y. Right? Got to double it. dx. Oh, but what's y equal to? That's why I drew the circle here. Because that equation is x squared plus y squared equal little r squared. So y is equal to the square root, little r squared minus x squared. Right? And I drew that deliberately so that the y would be positive and I didn't need to worry about a negative radical or anything like that. So 4 pi integrals minus little r to plus little r, capital R minus x times the square root of r squared minus x squared dx. Now supposedly you can do that without Calc 2 methods. Do you remember how we did it back then? Well, first we distributed and we created 2 integrals out of this. We multiplied capital R times that radical. We had 4 pi capital R then, integrals minus little r to little r, square root little r squared minus x squared dx, minus 4 pi integrals minus little r to plus little r, x square roots r squared minus x squared dx. And this was a real advantage to us because we did not do this integral. We said that integral is 0. Shucks. That was the S word I was going to use. How the hell did we know that? Odd function on a symmetric interval. Man, I got to give that guy extra credit for that answer. Right? You remember when you integrate an odd function from minus a to a? If it's odd, then that means that everything above the axis is balanced off by something below the axis. So negative area, positive area always cancels to a 0. And the way that we did this before was by interpreting it in terms of areas. We said, well, that integral is the area, right? Since it's the top, that square root is just the top half of this circle. So if we integrate the top half of that circle from minus little r to plus little r, we get half the area of the total circle. So back in Calc 1, we said 4 pi capital R. Now I want 1/2 the area of that circle, which is pi little r squared. So 2 pi squared capital R little r squared, and that was way back in Calc 1 we did that. Well, that was because back in Calc 1, we weren't ready for that, were we? Well, are we ready for it now? Can you do 4 pi capital R integrals minus little r to plus little r square root r squared minus x squared dx? Well, the first thing you ought to do is recognize that that's an even function on a symmetric interval. So I'm going to rewrite that as 8 pi r integrals 0 to little r square root r squared minus x squared dx. And now what I've been doing so far in setting up these trig functions, these trig substitutions, is to factor the r squared out. It's time to advance just a little bit here. Let's let x equal r sine theta. Well, what do I get then when I square x? R squared sine squared, I can just factor the r squared out, can't I? So dx is r cos theta d theta. This becomes 8 pi r, capital R. New limits of integration, when x is 0, theta is 0. When x is little r, sine theta is 1, pi over 2. This becomes square root r squared minus r squared sine squared theta. Dx is little r cosine theta d theta. So that little r comes out, square root of r squared is r. Multiply it times that, I get 8 pi little r squared capital R. So we're getting close here, aren't we? And then I've got the integral 0 to pi over 2 cosine squared theta. I'm skipping steps on you because we need a break. Supposedly you can finish. I'll let you verify that that's what you get. See you guys back here at 10 o'clock.